Alright, in this video, I'm going to cover section 13.2, which is about derivatives and integrals of vector functions. But in this video, I'll only take care of derivatives, and I'll cover integrals in the next video. Anyhow, so remember in the last video, I introduced the notion of vector functions, which is of the form like it's a vector where x component is a function of t, y component is a function of t, and z component is a function of t. And that gives a function of t, but the value of the function is actually a vector, and geometrically, this gives some kind of three-dimensional curve in R3. Okay, that's what the vector function was. Then now, in this section, what we're going to do is to differentiate and integrate vector functions. So let me start with the definition of derivative. Definition. So let R of t be f of t, g of t, h of t. It's a vector function. Then we define the derivative, which is often denoted by dr dt, which is also denoted by dr dt, is simply the derivative of each of the components. So you just differentiate each component like this. Okay. So in other words, this is, so to speak, component-wise differentiation. Okay, but what is this geometrically? So geometric meaning of the derivative of vector function. So remember, derivative in calculus 1, 2, like y is equal to f of x. If you take the derivative, that represents a slope of tangent line to the curve given by y is equal to f of x. Slope of the tangent line. That's what the derivative was. Then now, in the case of vector function, it has to do with tangent line. But it turns out that in this case, the derivative is basically a tangent vector of the curve of t. So the derivative itself is another vector. So it has to be a vector. But what kind of vector is that? Well, it's a vector which is tangent to r of t. Not r prime, r of t. Namely, this is a vector which is tangent to the curve represented by the vector function r of t. So geometrically, suppose this is r of t. And then if you look at particular point, let's say t, some arbitrary point t, and if you compute the derivative, you get a vector. But what kind of vector is that? It's a vector which is tangent to the curve. Okay. But why is that so? And here is a reason for this geometric meaning. So here's a reason. Let's remember the definition of derivative of the ordinary function. So this is just a differentiation of some single variable function. And you just take the derivative for each of the three components. So that means if you remember how to compute the derivative, if you remember the definition of derivative, so this is like a f prime of t by definition, g prime of t, and h prime of t. And that is, if you remember the definition of the derivative, that is equal to, let me write here. So remember how to compute the derivative? That is given by limit some small k goes to 0 of f of t plus k minus f of t divided by k. And then you have the same thing here for the other two terms, like this. Okay, then now, this is, how could you write it down? Well, this one is just, let's actually sort of factor out the limit and 1 over k, and this is written as limit k goes to 0, 1 over k, and then you have f of t plus k minus f of t, and the same thing here, like this. Okay, then what this is simply you can actually rewrite this as this: limit k goes to 0, 1 over k, and then you can actually sort of decompose this in the following way. Minus f of t, g of t, h of t. Right. Then now, what is this? Well, this is written as limit k goes to 0, 1 over k. And this vector is actually r over t plus k minus this vector here is just r of t. All right. So then this is written as, let me just write here, limit k goes to 0 and r of t plus k minus r of t divided by k. So now, what is this fraction? Well, let me write down the picture. Suppose this is our curve given by r of t. Then at time t, so remember r of t is essentially a trajectory of moving particle in a space for each given time t. And then suppose you are here at time t is equal to t, or arbitrary t. So that means here's the origin. This vector, the vector here, is r of t. That's this vector. Now how about this vector here? Well, the vector here is the position vector of the moving particle after k seconds. So that means maybe somewhere around here. So particle moves in this direction, let's say. And then after k seconds, or whatever the unit is, doesn't matter. K seconds, k minutes, doesn't matter. But after k seconds, you are here. So that's the position vector here. And that's this. And you take the difference. Well, what's this difference? The difference is actually the vector like this. This vector is r of t plus k minus r of t. Okay, then now, then you divide this by k, so that means you shrink this vector by some scalar, k. So you shrink it by dividing it by k. And this vector here is 1 over k and r of t plus k minus r of t. Okay. And then you take the limit. That means you get k smaller and smaller, smaller, that means what you do is to let this point get closer and closer to this point. Then what would happen? Well, then this line here gets closer and closer to the tangent vector. And that's what the derivative is. That's why the derivative is a tangent vector. All right. So that's a geometric meaning. But if you didn't really understand this logic, maybe okay, let's just know how to compute the derivative of vector function. That is done by just differentiating each component. And then geometrically, that is a vector tangent to the curve. So for example, let's do a simple example. Let r of t be 3 minus 2t, 4 plus 3t, and minus 1 plus 5t. All right, and then the derivative is you just differentiate each component by component-wise differentiation. So you differentiate this, what you get is negative 2, 3, 5. Okay, so that means that's a derivative. But what is this? Well, remember this is just a line. This is a parametric equation of a line. So this represents a line whose direction vector is negative 2, 3, 5. And after you differentiate it, what you get is negative 2, 3, 5. So that means this is simply the direction vector. For this example, this is a direction vector. And indeed, direction vector is a vector which is tangent to the line, because in this case, r of t is simply a line. And each arbitrary point, you compute a derivative, and what you get is direction vector, but direction vector is precisely the vector which is tangent to the line. Okay, so this sort of the reflects this statement. The derivative is a tangent vector. Okay, now, so if you compute the derivative, you get a tangent vector. That's fine, but the length of tangent vector is not necessarily 1. It might not be a unit vector, and then it is often useful to work with a unit vector. And then here's a definition. We define, okay, so given r of t, and we define t of t by the tangent vector which has a magnitude 1. That means if you compute the derivative, you get some vector which is tangent to the curve, but this might not be a unit vector. So you want to make it into a unit vector. And the technique to make a vector into a unit vector is to divide by its own magnitude. So let me just, I need more space. So it's written as this. And then this is a unit tangent vector. Unit tangent vector. So the idea is, like I said, if you compute the derivative, you get the tangent vector, and then you just pick up, you just either shrink or extend the vector to make that into a vector with length 1. That's what the unit tangent vector is. And then, but of course here, since we are dividing by the magnitude, we are assuming that the derivative, we assume that the derivative is not 0. And as we will see, this never happens in this. But first of all, you may always assume this. We are not going to encounter a situation like this in this course. And the derivative is 0. If the derivative is 0, that means indeed, as we will see actually in the next video, the section after next section, derivative is actually the velocity of the moving particle. So remember, r of t is the position of a moving particle, and then its derivative is actually the velocity. And then if derivative is 0, that means velocity is 0, which means the moving particle stops at some point. But we always assume that the particle never stops. But anyway, for now, don't worry about it. And moreover, I have to say this is just a 0 vector. We never encounter this situation. Anyhow, so let's just do an exercise. Example. Let r of t be cosine t, sine t, and t. Remember, we have seen this. This is a spiral or helix geometrically. It looks like going like this, going up the z-axis. And then now find the unit tangent vector. At this point, -1, 0, pi. Okay, here's the answer. So here's a definition of unit tangent vector in general. So first, we need to find t of t. Let's forget about this for now. Let's just find this by using the formula. To do this, the derivative is you just differentiate negative sine t, cosine t, and 1. Okay, and then you take the magnitude. To get the magnitude, you have to take the squares. Square, and take the square, and take the square root. And then, since sine squared cosine squared is 1, this is root 2. Okay, so therefore, the unit tangent vector is, by definition, you divide r prime by its magnitude. The magnitude is in this case root 2. So this is 1 over root 2 r prime t. And normally, this is a function of t. So what you see in the denominator is normally a function of t. But in this case, it just happens to be just a constant root 2. But anyway, this. And that is 1 over root 2 times this. Which is minus 1 over root 2 sine t, 1 over root 2 cosine t, and 1 over root 2. Okay. Then now, what we want to do is to find the unit tangent vector at this particular point. Okay, this is a unit tangent vector at an arbitrary t. So we want to find the unit tangent vector at this particular point. But now, what's t in this case? So that means we have to find a particular t that gives you this point. Well, r of t is this one. So we want to find the t so that this r of t is equal to this. And by looking at, for this case, the second component, third component is t, and that's pi. So therefore, what you have to do is to find t of pi. And that is, so you just plug in pi here, and then what you get is 0, negative 1 over root 2, and 1 over root 2. So that's the answer. So let me just note here as a side remark. R of pi is negative 1, 0, pi. And then pictorially, like I said, this curve is a helix, it's spiral. And t is equal to 0, you are here actually. And then you just move up like this. And then at t is equal to pi, you will extend this. And t is equal to pi, you are somewhere around here. Okay, so this is t is equal to pi. Okay, that corresponds to the point negative 1, 0, pi. And then what you computed here is the vector tangent to this curve. So it's a vector like this with magnitude 1. So that's what you computed. Okay, so that's about the unit tangent vector. And now, as a last thing for this lecture, let me actually list some of the properties of the derivative. So given vector functions, two vector functions, u and t, v. Instead of using r, let me use u and v. U of t, v of t. Property number 1, you add two of those vector functions and take the derivative, and that's the same as. And this is sort of the, it should be sort of obvious, because what you do to compute each of those is to differentiate component-wise. So if you add components first, take the derivative, that's the same as taking the derivatives first and add the two vectors. All right, 2. If you multiply scalar c is a scalar, to a vector function, and then take the derivative, that's the same as you first multiply the scalar and take the derivative for scalar c. Okay. This is also obvious because what you do to multiply c to a vector function is you just multiply the scalar c to each component and take the derivative. Now 3. As a sort of like a generalization of this, as a more general case for number 2, what if c is a function of t, namely for a scalar function, meaning just a function whose value is a scalar. In order to distinguish a scalar function from vector function, we just emphasize that by saying scalar function. That means this is a function whose value is a scalar. If you multiply scalar function to u of t and take the derivative, that's the same as you take the derivative of the scalar function and plus do like this. Okay, and then now, number 4. This is interesting. U of t dot v of t. So u of t and v of t are two vectors in R3, or could be R2. And so you can take the dot product and take the derivative. And that's the same as u prime t dot vt plus So for the derivatives of vector functions, Leibniz rule basically applies to dot product. And similarly, the same thing happens even for the cross product. Take the derivative, and that's the same as u prime of t cross v of t plus u of t cross v prime of t. And finally, if you differentiate u f of t, namely you plug in a function of t to the variable for u, and then you differentiate it, and this is the same as, first you differentiate u, and then just plug in f of t, and then multiply f prime t. So this is chain rule. This is a chain rule. And then you can actually verify those formulas by yourself. But for this, let me just do number 4. And the other cases can be sort of proven in a similar way. So let's just do number 4. I'll do number 4. So here's a way to write down the proof like this. So you have to do it in general. You can't just pick up particular vectors or anything. Just do it in general. So let u be f1t, g1t, and h1t, and vv, or u of t, to be precise, and v of t be f2t, g2t, and h2t. Okay, and then let's just compute the dot product. The dot product of those two is what? This is just a product of those. So f1t, f2t plus g1t, g2t plus h1t, h2t. So that's a dot product. And then you take the derivative. And then notice that this is just a function. It's a regular function. It's a scalar function. It's not a vector function anymore. It's just a function. It's a scalar function. So when you compute the derivative, you can just compute in the way you do in calculus 1 or 2. So you just differentiate each of those. Okay, then what do you get? Well, you just apply the Leibniz rule for each of those, and then you get f1 prime of t, f2 t, plus f1 t, f2 prime of t, and the same for g and h, like this one. Okay, and then you can actually group them together by picking up this part, and this part. And then what do you see? Well, you will see f1 prime of t, f2 t plus g1 prime of t, g2 t plus h1 prime of t, h2 t. Okay. So this part is here, here, and here. And the remaining terms are those. And they give you this. So this is the other three terms. And now if you look at each of those, you notice that this is written as indeed f1 prime of t, g1 prime of t, and h1 prime of t dot f2t, g2t, and h2t for the first term, and then the second term is written as f1t, g1t, and h1t dot f2 prime t, g2 prime t, h2 prime t. Okay, and then you will see that this is indeed written as u prime of t dot v of t plus u of t dot v prime of t. Okay, so that's the way to prove this. And in a similar way, you can actually verify all the other formulas appearing here in this way. You can just verify it. And the verification is your exercise. Okay, so that's all for this section. And in the next, for this video, like I said, in the next video, I'll cover integration of vector functions.